From the MIT Energy Initiative, this is What If It Works, looking at the energy solutions for climate change. I'm Kara Miller.
And I'm Rob Stoner.
And today we're joined by Moungi Bawendi. He's a professor of chemistry at MIT who has thought a lot about creative ways to reimagine clean energy technologies. He also recently received the Nobel Prize. He's a co-winner of the 2023 prize in chemistry. Bawendi's early research led to more energy-efficient lighting and televisions, but also to lots of work on creating more efficient solar cells. As a postdoctoral student, he worked in the famed Bell Labs, a place where he says he learned a lot about chemistry, in part because there just weren't that many people around to help him out.
It was an amazing place because it was populated with extremely talented, ambitious scientists that were giving a lot of trust and a lot of free rein. It was a place that had a lot of equipment, but not many hands. As a result, you had to build a community if you wanted to get anything done. So everybody was happy to talk to anybody else. In fact, it was part of the job to talk to everybody. There was no army of graduate students. It was each scientist with a technician and maybe a postdoc, and that was pretty much it.
What that meant, Bawendi says, is that he learned a ton. Now, by contrast, he does a lot of paperwork in order to have the funds to keep his lab running and to support his doctoral and postdoctoral students. At Bell Labs, he spent a great deal of his time just thinking about science.
What I didn't know much about, or really very much at all about, was synthetic chemistry, making things, I was a measurement person. But at Bell Labs, in the atmosphere of Bell Labs, you were allowed and encouraged to learn new things and to try new things. And I worked in Mike Steigerwald's lab, who was an organic metallic chemist, makes molecules. And he taught me everything I know about chemistry, how to make molecules, using inorganic chemistry. And then from Bill Wilson, who's now at Harvard, who was a laser expert, I learned everything about visible lasers from him. And from Lewis, I learned how to think. Bruce was sort of the chief thinker.
It was at Bell Labs that Bawendi started working on something that would eventually be called quantum dots. Here he is explaining what a quantum dot is.
The quantum part of quantum dot is because the electron that you put in the quantum dot no longer acts like a little particle moving in a wire. It behaves like a wave. That's the magical part of quantum mechanics. That's when you get to really small scales. Things that you think of as particles are now described by waves.
Okay, so now that you're trying to get your head around the idea that tiny, tiny particles are, in some sense, waves, think back for a minute to your junior high school band and the various instruments in that band. Why did they sound the way they did?
So if you look at a flute or a piccolo, you know that the sound of a flute or a piccolo are really different. The flute is lower pitch than the piccolo. And why is that? Because the sound wave in a flute has a bigger cavity than a piccolo. And for organ pipes, it's the same thing. So a little tiny organ pipe sounds much higher pitched than a big organ pipe. Mm-hmm. And so you can think of the electron in the quantum dot in the same way. The wave of the electron has a different pitch depending on the size of the dot, just like for the organ pipe. And what does pitch mean for an electron? It's the energy. So the energy of an electron in a small box is higher than the energy of an electron in a big box.
Bawendi says that when the electron releases its energy, it turns into a wave, a light wave. High energy colors tend to be blue, and low energy colors tend to be red.
You've got your rainbow. So the higher energy electron gives rise to bluer light coming out, and the lower energy. So there's your size effect right there, right? From small to large, just like in an organ pipe. So if you think of the sound as being colors, then the high-pitched little organ pipe is blue, and the low-pitched big organ pipe is red.
The work on quantum dots was part of a quest to make better quality materials for communication, because Bell Labs was, after all, part of a telephone company. But it would be a while before Bawendi realized that the work he was doing might have implications for clean energy. When he first had a sense that it could, he was collaborating with a chemical engineer who had friends at the tech company Hewlett-Packard.
And so he had a supply of these brand new lab-based gallium nitride diodes. The first thing that we tried, I mixed the quantum dots in polymer and put them on top of the blue diode to change the color because there was a big push to create more efficient lighting, white light. So by mixing different colors of dots together and pumping them with this very efficient blue light source, we could make white light. And that was really the beginning of me thinking about the dots in the energy world. And that was the late 90s. And we wrote a paper, I think, around 2000 or 2002 on that.
Quantum dots are now used widely in televisions. And as they've made us more energy efficient, the irony is our appetite for them has grown.
Especially in outdoor, in a bright room. So there's room for expansion in the screen business to make more and more screens bigger and bigger and brighter. The quantum dots are used in the screens, again, as a way of color shifting. So you use a source of blue light, either gallium nitride diodes or blue OLEDs in the newer televisions, and use the quantum dots to create all the other colors in a very energy efficient manner, because you only create the colors that you need, as opposed to the previous generations of television where you created white and then you filtered out the colors you didn't need. So you wasted a lot of energy in all these colors that you just threw out. And so now we have much more energy efficient, much nicer colors, better colors. And what happened is that the televisions just get bigger and bigger. They just use the same energy, maybe a little less, but they just get bigger and brighter. And then you can use them in a sunny day and in your room.
It reminds me a little bit of when the manufacturing of clothes got mechanized. People went from maybe having 3 outfits to having like 50 outfits, right? Because and so
humans find a way.
Exactly. So it's interesting that, just because you can make lights or televisions more efficient, then we say, okay, great. Then we're going to double that screen size because why not?
Yeah.
Who doesn't want a bigger television?
So that's a mission where we're making light using these things or shifting light into a range of colors that we want.
Yeah.
But you've also used quantum dots in solar cells to capture light and make electricity, right?
Sure. So I think I started going into that soon after, probably the mid-2000s. And the idea first was to make photodetectors, because you could then really tune the sweet spot of that photodetector to particular wavelengths.
What is a photodetector?
Something that turns light into electricity.
Okay. Light
in, electricity out. And that then morphed into solar, because, light into electricity. And our first foray, and I was doing this with a colleague, Vladimir Bulovich, whom I've had a long-standing collaboration, starting from 2000, basically. The quantum dots had, because you can tune what they absorb in terms of color, you can tune them so that they are in the sweet spot for the solar spectrum, for converting as much of the solar spectrum as you can. And solar is actually a very slow moving field, because you've got an established material, silicon, that works really, really well. And the cost of silicon, follows a law called Swanson's law, which is that the cost goes down by 20% for every doubling in production. That's been going on for 70 years. It's the solar equivalent of Moore's law.
I was going to say, I know Moore's law, but Swanson's law, I'm going to have to add to it. Okay.
Anytime you have a mature technology, there's this kind of law associated with it. It's basically a scaling law. The more you make, the cheaper it is, basically.
So that scaling is largely taking place in China.
Right now, it's taking place in China, right.
And so the whole U.S. industry where silicon photovoltaics began has moved away. And does using quantum dots to create different sorts of panels offer the possibility of reshoring that to some extent?
So what we've learned from the quantum dots is that using them as the functional material to replace silicon is probably not going to be cost effective. because silicon is so cheap. So the cost of anything depends on the number of steps you need to make it. The more steps, the more expensive it is. Silicon, you process the silicon and you make it pretty much in one step, You crystallize the silicon and you cut it in pieces. With the dots, you have to make the dots first. Then you have to process them. And so you got a few steps in there. And some of the components of making the dots may not be very cheap. So everything in solar needs to be really, really inexpensive. And the quantum dots as a functional material, I don't think are going to be inexpensive enough to replace silicon. But they can add to it. For instance, silicon doesn't absorb very well in the UV or the blue. But the quantum dots can, and they can re-emit light that silicon can absorb really well. So you can combine them, not as the functional material, but as this downshifting material.
So you're going out and getting more light that you can bring into the range that can be absorbed by the cell.
The silicon can absorb better.
So you'd have both of them existing, like if you were talking about a solar panel that went on a building or something, or in a field or whatever, they would both exist, both the silicon and the quantum.
One would enhance the other.
So they're directly on top of those cells?
Or the bottom.
Uh-huh. Those are called tandem cells, if I understand right.
So the bottom are called bidirectional or bifacial cells.
Bifacial
cells, yeah.
And they're making those now, right?
Bifacial cells are existing, yes. They're going online, yeah. So traditionally, you think of a silicon panel as absorbing light from above, directly from the sun. But there's all this light that's being reflected from the ground that comes back up from the ground. Okay. So if you can capture some of that light, you can increase the amount of electricity.
I see. So when you say bifacial, you're really talking about like this is a double-sided
solar cell.
Right. Instead of, exactly, is what we think of as like we see them on a house. The thing that goes up towards the sun is the thing that matters. But you're saying like, no, you can make the thing that's on the underside matter too.
Yeah. And then you can use dots on either side to help you catch more of the light that you need in order to increase the efficiency of the panel. And if you increase the efficiency of a silicon panel from, let's say, 21% to 22%, that's real money. It sounds like a 5% change. But if you go from 21% to 23%, you say, that's 2% change. But that's actually a 10% change in the amount of electricity that comes out. That's real.
Right.
When are these things coming? When can I go out to Alti and
buy
her
quantum like I said, solar is slow moving because silicon works so well. Not only does it work so well, it's extremely stable. So anything that we add to silicon has to last as long as the silicon panel, which is 30 years or even more. And so that's where you get the problem. That's a challenge.
So you have to end up engineering protective layers. And
that costs money.
It just gets harder, I see.
Right. Yeah. So there are all these ideas that are extremely interesting ideas from a science or technology perspective. But then when you add the layer of the commercialization, the business part of it, then you have to realize, some things are just not going to be worth it because they're never going to be cost effective, and others, they could become cost effective, but it's going to take some work. There's another application, which is an interesting application that there's a small company out of Arizona that's pursuing. It's not a new application, but they're really pushing it forward. It's for agriculture. So when plants grow, they like light, photosynthesis, right? But they don't like a lot of UV light or blue light because it burns the plants. So you can actually have better yield of your crops if you take some of that blue light or UV light and turn it into red light. So they're coming out with these very inexpensive products that are basically films, plastic with quantum dots embedded in them, that you throw inside a greenhouse. They will take some of the blue light, re-emit it as red light, and increase the yield of crop production by 20% to 25%. It's just amazing.
Oh. So this is, if I owned a greenhouse and I was going to get this is just some sort of film or something that you've got your windows in your greenhouse and you put it there so that when the light comes in from the sun, there's a little bit of fiddling with it from the quantum dots, and then the plants are happier and grow better.
Exactly. Yeah.
They just see a brighter light in the spectral range that they
That
want.
they like. Yeah. Yeah.
I mean, in some ways, that also contributes a lot to energy efficiency, because if you can grow fewer plants, right, fertilize less, and you get a better yield, just you didn't really have to do anything too fancy.
Absolutely. And initially, the application in greenhouses was, okay, so we're going to filter out some of the blue lights that the plants don't like, take some of that red emitted light and make electricity out of it, and then power fans.
So that improves the economics.
Which would improve the economics.
Mm-hmm.
But it's not clear that that's the best way of the dots either, because, okay, so you power fans with light that you filtered out, but maybe, all you need is a little tiny silicon PV that you put to the side of the greenhouse. You get the same result, and then you filter out the light with something cheaper. So the economics of combining the two together, trying to make something do two things at once, may not be quite right. And that's how they got to the idea, well, the plants like red light. We've got these films that we created. It's much easier to make a film that doesn't waveguide, that just re-emits, than to try to make it turn into electricity, which then you can use maybe to power red LEDs to make more red light. So let's just make a product that makes one thing really well.
Instead of making a film, coating a film with quantum dots, could you make a spray that actually coats the plant, say the corn? Or are they too expensive or too toxic?
I was going to say, or coats the window. Could you spray the...
Coat the window,
Yeah, coating the windows is another way, or integrating the dots directly into the window. So the next thing is going to be to make the windows directly. So you don't have to buy a film. You make the windows with dots in them.
Uh-huh.
Are people doing this in their greenhouses yet, or is this not in commercialization land yet?
It's in the testing phase.
Okay.
So, there are contracts from the government, from NASA, from other places. There are collaborations between large companies and these startups to do that. And it's in the a phase where they're demonstrating the possibilities. And then, whether it's going to be adopted is always, it's in the marketplace.
We've talked about different companies doing different things with quantum dots. Just give me a sense. Obviously, this is something that you did initially, but now it's like way beyond you. It's sort of out there in the public domain. Are there hundreds of companies that are working on things related to quantum dots in all different realms, or do you have a sense? Or
yeah, I would say there are probably hundreds of companies.
Okay.
Yeah, all over the world.
And what
large and small. And
what are the big, like if we were to look at a pie chart of what they were doing, what are the big, chunks of things, like the main things that those companies are doing with the quantum dots?
The biggest thing is screens, display screens.
For televisions.
For televisions, for laptops, for displays of all sorts, automotive, whatever.
Okay.
That's the biggest. So they're made the dots are made in huge factories and on a huge scale for that.
How much do quantum dots add to the cost of a computer screen? Is it a big fraction?
No, it's tiny. I would say probably there are two huge manufacturers of dots right now that provide essentially all the dots that are in the marketplace. And one of them is Samsung.
Okay.
Or Hansol Chemicals, which is part of the Samsung business. And then there's a Japanese company, Shoei Chemicals, and they provide. And then there are all these little startups that are trying to work in that field.
But it's interesting because you said the cost may make it really difficult to compete with like the incumbent solar panels, that they're like, people know how to do them. It's cheap. It's fine. But then if they're so widely used in computer screens and television screens, why is that cost effective? But like solar panels, like maybe that won't work out.
The kind of dots that are made for the screens are made to emit light really efficiently. If you want to make dots for solar panels, they also have to conduct electricity really efficiently. The amount of dots you need to make light in a screen is pretty small. The same thing for the agribusiness, because really all you need to absorb is a little bit of blue light, some of the blue light. In the solar panel, you want to absorb all of the colors, the whole solar spectrum. You need a lot more material. And then you're competing with the silicon, and you're competing with the stability of silicon. The stability of the dots in the TVs is actually incredibly good.
Meaning they'll last for a long time.
They're going to last forever.
Mm-hmm.
In a solar environment, you need to create electrons. Whenever you have electrons around, you can do chemistry with those electrons. And that's the part that's really hard with the dots, to make them last 30 years in the presence of all these electrons.
Now, you've also used quantum dots in a number of biological applications as well. Talk about that a little bit.
That actually was the first commercial application of quantum dots, which is a little backwards when you think about it, because it's a really hard application. Yes. The TVs is really easy in comparison, because we make the dots in organic solvents, meaning not in water. Then you have to work really hard to get the dots into water, into a biological environment, and protect them.
You could inject them into somebody and they would go to some place where you would image them, for example.
Yeah, so the first application was with cell imaging. You target different parts of a cell, and you see it in the emission, in the light that comes out, and you can map out a cell. Very similar to what had already been happening with dye molecules, and we use dye molecules for this all the time. And now the first company was started in 98. I helped start that company, Quantum Dot Corporation. The dots are part of Thermo Fisher. You can just buy the dots from Thermo Fisher for biological applications. And so there's still a market for them. And we've used them also for in vivo imaging with animal models of cancer, to understand the microenvironment of a tumor, to understand blood flow in tumors, with collaborations with folks at MGH, at Harvard Medical School.
So you're like dyeing these little things so that people then can track, right, what's happening in these cells, or is that right? Okay.
Yeah, you can peek into the microscopic details of what's happening in a tumor. What we learned in the animal experiments with the quantum dots really fed into the design of what we used in humans. So it's good to remember that the time scale from discovery to an application is really long, decades. The average gap between the discovery, the invention, and the awarding of the Nobel Prize on average is 30 years. It just takes time for the impact to be seen. There's so much work that goes from the initial idea and the discovery to getting something that's actually working well, that society can use, day to day.
So when you think down the road about the work that you've done, and you think about clean energy and energy efficiency, which is, I know, very important to you, where do you think like that biggest impact of your work will ultimately be felt, even if it isn't felt yet?
I mean, there are two answers to that. One of them is, I have no idea.
Good answer.
So humans are pretty good at looking 3 years ahead. They're really terrible at looking 20 years ahead. We just have no idea what's the world will be like technologically 20 years from now. If you look back, 20 years ago, we were just wrong about most everything, right?
Right.
So it's really hard to know for sure. So I bet I can tell you in the next 3 to 5 years, I think this downshifting business, maybe in agriculture or in increasing the efficiency of solar, maybe in 5 to 10 years, maybe that will have an impact.
So the sort of films of in a greenhouse of filtering out the light that the plants don't like, and so increasing yields that way. And then maybe in a few years that there will be a real impact on the efficiency of solar.
Yes.
It sounds like, I mean, I don't have a good sense. Rob, I'm sure you've seen a million efforts to do solar. You were talking about like it being 20% efficient, and maybe quantum dots taking it to 22 or something. I know this is a silly question, but where's like the 50% or the 60%?
Come on.
I think there's like a long way between 20 and 100, but I'm not sure.
Yeah, no, but people are working on that. Those will be tandem cells where you have multiple PV cells that absorb different parts of the spectrum.
Okay.
And then you can raise that to the 40% range, which would be just, incredible.
Right.
That isn't necessarily quantum dots.
Not necessarily quantum dots.
You mentioned perovskites.
Perovskites. So that's part of my research, actually.
Okay.
Taking silicon and adding on top of silicon a thin film of these materials called perovskite thin film solar.
Which is what?
These are thin films of this material that you can make essentially in one step with earth-abundant materials near room temperature. So it's really inexpensive and easy to make. You can add on principle on top of a silicon cell and raise it from 20% to 30%. It's been demonstrated above 33% now, and there's no reason why it couldn't be in the 40% range theoretically.
These are also sort of tunable materials in the sense that you can modify their properties in order to capture a particular part of the solar spectrum.
Yeah, so that's why I don't work on quantum dots for solar in that business anymore, because this perovskite have taken over. They're much cheaper, much easier to make from a cost perspective. They're just as tunable. And they could be, maybe in 10 years, you could start seeing real tandem cells that would be in utility grade applications, solar fields, where you're getting 28%, 30% power conversion efficiency, real
That
increase
seems like a game
efficiency.
changer. 50% increase in.
That would be a game changer, yes. So the issue with those materials is the stability. How long do you need it to be? Because if it's inexpensive enough, maybe you can just replace that part every 10 years and keep the silicon under it. But that replacement is going to require labor. So that's going to be a cost. So the economics of it are not completely clear. I mean, it would be best if they could last 30 years. And so the whole thing lasts 30 years. And the big solar companies are all working on this because they think that this could be really important for the future.
Got it.
And so they're putting in hundreds of millions of dollars into that space. And they may at some point start gobbling up the startups for their technology.
Which is a good thing.
Which is absolutely a good thing. Absolutely a good thing.
So what if it works? I mean, solar panels get, cheaper, maybe, for every watt of electricity they produce?
Yeah.
They maybe get smaller?
Smaller or cheaper. It depends on the application. I think for perovskite, I think the solar fields is the right application for them. People talk about flexible PVs that are ubiquitous, etc. I'm not sure that perovskites are going to be able to do that for the one reason is that they contain lead. Uh-huh. And that's going to be a lead, yeah. Okay. That's a non-starter, I think, for anything that's consumer related.
Okay.
But for solar fields, there was plenty of lead in big silicon panels out there, and cadmium telluride is a big material for solar fields, and it's contained and it's recycled and it's not going anywhere, and it's not a problem.
It's kind of like you have a differentiated marketplace in vehicles, right? Just because you might put a certain kind of fuel in like a big rig doesn't mean that's what you put in your little car. I mean, it sounds like, the solar panels you might put on your house on the side that faces the sun is not necessarily what you would have in like a huge industrial solar field. Yeah. So when you think about your own views about clean energy, where are you in terms of optimism, pessimism, how you think about our journey towards clean energy?
Oh, in terms of the technology, I'm quite optimistic.
Yeah.
For two reasons. One of them, we already have the tools today. Silicon works incredibly well. Wind power works incredibly well. They scale up. You look at the cost. I mean, Swanson's law again, 20% lower cost every double of production. You just follow the line down, and it crossed fossil fuel in most part of the world already, and you keep falling down, and there's really no real reason why suddenly it should saturate and say, stop falling down. It's just such a mature technology. So just from that perspective, it's incredibly optimistic. And then all these add-ons, all these other technologies that are coming on board, we don't need all of them to work. We just need a fraction of them to succeed. In the end, it's policy. Are we going to use the technologies we have or that we create, or are we just going to, it becomes policy, it becomes politics. The problem is that in terms of basic science, when we are at the beginning of discovery, the support for that has been less and less over the last 30 years, independent of what field it is.
This is just the NSF doesn't get as much money as it should. Is that the situation? Or?
Yeah, the budget of the NSF has not followed inflation by any means over the last 30 years. What could fund research from an NSF grant when I started is what we get now is about a quarter of what we used to get in terms of real dollars.
Wow.
It's really, I talk to my colleagues all over the US, and we think that, we could do what we could do before, but now it's really critical now. It's not sustainable. Mm-hmm. And that was the beauty of Bell Labs.
Yeah.
It allowed people to really explore with little accountability.
Right.
It was trust. Trust that, you guys are really smart. You think of really hard problems. We trust you that you're going to come up with something interesting.
Yeah. I think in the early 60s, the government spent like 2% of the budget on science and research. This was like a lot of it was to get to the moon. When you talk about the heyday, that had all sorts of ripple effects out. And I don't think it's anything close to a couple of percentage points now.
And if you think that it takes 20 or 30 years to reap the benefits of that investment, 1960 plus 30 is 1990. And
yeah, we're not feeling the pain.
We're not replenishing our pipeline of basic discoveries that are going to change the world.
Right.
Do you think it can shift to the private sector? A lot of the work.
That's an argument that I've heard.
Yeah.
I've heard that argument. And maybe in biotech, there's a lot of research going on today that is more basic than there's a lot of money in biotech and they're doing really amazing things. I don't think the private sector has the timeline that is needed for basic research. It's just not in the cards. Bell Labs was an anomaly. Bell Labs was an anomaly because it was funded by AT&T, which had a monopoly on the long-distance network and was just making money right and left and had the ability to do that, to really do that. And when the monopoly was broken, Bell Labs disappeared.
The other big monopoly around that time was IBM's monopoly in the large computer business.
Exactly. And the Yorktown Heights was an example of the amount of research that came out. Yeah. It was just amazing.
Yeah, and it's also faded away.
It's all gone. Yeah, it's pretty much all gone. Mm-hmm. And when the big oil companies, really were making a lot of money, like Exxon had a research lab where they studied fluid dynamics and all sorts of things. Very, really active place. That's pretty much disappeared as well.
Yeah. And the oil and gas companies still do fund a lot of university research. It's not necessarily received graciously or gratefully in some quarters, but I'm just recalling that they have funded a great deal of solar research at
Absolutely.
MIT. They're very active in plasma science and in fusion research and other areas.
I think they see, they are used to looking at long time scales. When you develop an oil field, it takes decades from the initial find to developing. You're talking about 30 years, right? And so they're used to really long time scales, and they see their business 40 years from now. What is it going to look like? It's going to be really different. So they know they have to switch.
Yeah.
And parts of them are funding things that could allow them to switch.
Moungi Bawendi is professor of chemistry at MIT. He's also the winner of the 2023 Nobel Prize in Chemistry. Thanks so much. It's a really fun conversation.
My pleasure.
Thanks, Moungi.
What If It Works is a production of the MIT Energy Initiative. If you like the show, please leave us a review or invite a friend to listen. And remember to subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts. You can find an archive of every episode, all of our show notes, and a lot more at energy.mit.edu/podcasts. And you can learn more about the work of the Energy Initiative and the energy transition at energy.mit.edu. Our original podcast artwork is by Zeitler Design. Special thanks to all the people at Mighty and MIT who make this show possible. I'm Kara Miller.
And I'm Rob Stoner.
Thanks for listening.